System of particles. In this topic, we assume the system as the combination of n number of particles and we derive the relation among these quantities. And again, I am not going to introduce any basic concepts and I am not going to develop the idea from basics onwards. So to understand this topic, you should have some minimum knowledge about these terms. That is laboratory frame of reference, center of mass frame of reference, position vector, velocity and linear momentum, acceleration and force, kinetic energy and work energy theorem. Here, what do you mean by laboratory frame of reference? Brief explanation. It is fixed reference frame. Example, the frame fixed to the ground. And we know Newton's laws are applicable with respect to this frame. And the center of mass frame. This reference frame is fixed at the center of mass of system of particles. That is, the frame with its origin at center of mass of system of particles is called center of mass frame of reference. Here the system means the system contains n number of particles, right? Now let m1, m2, m3, m4 and so on are masses of particles within the system, and r1 bar, r2 bar, r3 bar, r4 bar and so on are their position vectors of particles which we treat as a system, and these position vectors are with respect to laboratory frame of reference. Now we know the definition of position vector. Now here the system which contains n number of particles. Let m1, m2, m3 and so on n number of particles the system contains, and their respective position vectors are r1 bar, r2 bar and so on with respect to this laboratory frame of reference. And here C is the center of mass of system of particles, and RC bar is the position vector of center of mass. Then as per the definition of center of mass of position vector, RC bar is equal to m1 r1 bar plus m2 r2 bar plus m3 r3 bar plus m4 r4 bar and so on, whole by m1 plus m2 plus m3 plus m4 plus and so on. This can be written as summation of mi ri bar by summation mi. Summation mi can be taken as total mass of the system, and I am taking this to this side. So capital M RC bar is equal to summation mi ri bar. So this side, this is called algebraic sum of moment of masses, that is equal to capital M RC bar. And this is about laboratory frame of reference, as I told you. But we know Ri bar is equal to ith particle. I is ith particle and Ri bar is position vector of ith particle with respect to laboratory frame. And we know this is the position vector of center of mass of system of particles with respect to laboratory frame. And here ith particle position vector with respect to center of mass frame means the reference frame which is fixed at center of mass, that is center of mass frame. So Ri bar is equal to Ric bar plus Rc bar. And now I am substituting in equation number 1, m Rc bar is equal to here summation mi. Next Ri is replaced with this Ric bar plus Rc bar. M Rc bar is equal to summation mi, just expand Ric bar plus summation mi Rc bar. Here m Rc bar is equal to summation mi Ric bar plus m Rc bar. Here Rc bar is fixed, that is with respect to laboratory frame. I am taking this outside, so summation mi can be written as total mass. Now this term and this term gets cancelled, then you get this, that is summation mi Ric bar is equal to 0. This is algebraic sum of moment of masses but with respect to center of mass, that is equal to 0. Algebraic sum of moment of masses about center of mass is equal to 0. That is with respect to center of mass frame, that we know. Here is the clear explanation. Here the graph, this is laboratory frame, this is center of mass frame, and here ith particle position vector is Ri bar, and the center of mass position vector is Rc bar with respect to laboratory frame, and here Ric bar is position vector of ith particle with respect to center of mass. The discussion started here, and clear picturization here. Next, what about velocity of center of mass? And this formula we know, Vc bar is equal to summation mi Vi bar by summation mi. That means this is a laboratory frame. M1 particle moves with velocity v1 and M2 particle moves with velocity v2 in different directions. So okay, different particles moves in different directions, and the center of mass of this system of particles moves with velocity Vc bar. Then the center of mass velocity Vc is equal to Vc bar is equal to summation mi Vi bar by summation mi. Summation mi can be written as total mass. So here I'm taking this term to this side. So capital M Vc same, and capital M Vc is equal to summation. This is ith particle mass, ith particle velocity with respect to laboratory frame. So ith particle linear momentum with respect to center of mass, and summation gives you total system. Summation Pi is linear momentum of system with respect to laboratory frame. But we know this Vi is equal to Vic plus Vc. So Vi is ith particle velocity with respect to laboratory frame, and center of mass velocity with respect to laboratory frame, and here ith particle velocity with respect to center of mass frame. Here this is center of mass frame, and here is the ith particle velocity. Let me take this is ith particle, and ith particle velocity and mass of ith particle. Now this is center of mass velocity, right? Now I am taking with respect to center of mass, so minus Vc bar, and the resultant vector is Vic bar. So here this is, if you expand, you will be getting summation mi Ric bar plus summation mi Vc bar. Vc bar you take outside, and the total mass you get. These two terms gets cancelled, and you will be getting this. That is a linear momentum of system of particles about center of mass is 0. That means with respect to center of mass frame. Center of mass frame is also called as zero momentum frame. Why? Because linear momentum of the system of particles with respect to center of mass is equal to 0. That is the reason. Next, let us take any two particles. Linear momentum of two particles system with respect to center of mass frame, any number of particles, it is 0. That we know. Here we have proved, because here we have concluded, right? For n number of particles it is 0. Algebraic sum of linear momentum of system of particles. Here even for two particles also we get 0, but different terms let us understand. Here first particle linear momentum with respect to center of mass. Now m1, and with respect to center of mass, that's why I'm taking velocity of first particle with respect to center of mass, and this relation we know, v1 is equal to v1c plus vc bar, vector form. Next, v1c is equal to v1 minus vc. You can substitute here v1 into v1 bar, m1 into v1 bar here, and vc bar is this, right, for two particle system. If you expand, you will be getting this. Here m1 v1 bar plus m2 v2 bar minus m1 v1 bar plus m1 v1 bar minus m1 cancel, right? So m2 v2 bar minus m2 v1 bar minus m2 v2 bar. So after multiplying with this, you will be getting m1 m2 into v1 bar minus v2 bar by m1 plus m2. This is called reduced mass mu, and here v12 1 with respect to 2 as per definition, relative motion. Now similarly we get p2c is equal to this radiation mass into 2 with respect to 1. Here 1 with respect to 2 when we calculated 1 with respect to C, then here 2 with respect to C means here. So you'll be getting, once you try, here mu is equal to m1 m2 by m1 plus m2 is reduced mass. And one more thing, what is the total linear momentum of the two particle system? Mu into v12 here plus this, but we know v12 is opposite vector to v21, then we get 0. That is the conclusions are P1C plus P2C equal to 0 for two particle system, and summation Pi is equal to 0 for system of particles. Here therefore neither internal or external forces change the momentum of system of particles with respect to center of mass. Okay, that is the final conclusion. Next, what about the acceleration of center of mass? Here let us take, this is a laboratory frame, and I am taking first particle, and here this is second particle, third particle, and so on. This is ith particle, and m1 is acted upon by f1 external force, m2 is acted upon by f2 external force, m3 is acted upon by f3 external force, and finally the ith particle means a general particle that I am selecting. Ith particle is experienced by an external force Fi bar, right? Now we know there are mutual interactions among different particles. This first particle applies force on this ith particle, and even ith particle applies force on first particle. Similarly, second particle applies force on ith particle, and the ith particle applies force on second particle. Next, third particle applies force on ith particle, and ith particle applies force on third particle, right? Only I am identifying the forces acting on the ith particle by just taking 3 particles as an example, but if you take n number of particles, this one particle is experienced by that many number of forces. Same way, this first particle also get experienced by that many internal forces along with this external. Similarly for m2 and m3. Yes, here AC bar is equal to m1 a1 bar plus m2 a2 bar plus and so on by m1 plus m2 plus and so on, right? This can be written as summation mi ai bar by summation mi. So this is total mass capital M AC bar is equal to summation mi ai bar, right? But motion of an individual particle, ith particle, let us take with respect to laboratory frame. Yes, mass of ith particle and acceleration of ith particle is equal to force acting on the ith particle. On ith particle, how many forces are acting? One is external force, that is Fi bar, plus on ith particle by first particle, on ith particle by second, on ith particle by third, and so on. Means by n number of particles. Ith particle ij cap f ij, and here j value changes from 1 to n. That's it. Here summation j1 to n Fij bar is equal to internal forces acting on ith particle by remaining particles. Here the same particle won't apply force on the same particle, right, on itself. That's why I should not equal to j. That's it. Motion of system of particles is, this is only force acting on ith particle. If you want to go for motion of system of all particles, just to go for summation on both sides. So summation mi ai bar and I equal to 1 to n again. Same way here I did not write. Here right side summation I equal to 1 to n, and this part, alright, just expand on right hand side. And anyway, summation mi ai is equal to, here from equation number 1 we know mac bar is equal to summation I equal to 1 to n fi bar plus summation I equal to 1 to n, here summation j equal to 1 to n and Fij bar, right? Equation number 3. Next, here this second term actually algebraic sum of all internal forces, right? Here sum of all internal forces are acting on all system of particles. If you take from here to here, this is the net force acting on ith particle by other particles, means internal forces only, but on ith particle. If we take this on all the particles of the system, sum of all internal forces acting on all system of particles by other particles, which is equal to 0 as per Newton's third law. That means here F12 is equal to minus F21, F13 equal to minus F31, and so on. Fij is equal to minus Fji, and so on. And even this is not possible, that we told, right? Next, so from this what we can write, MAC is equal to summation I equal to 1 to n Fi bar you have, and net external force acting on the system, this is, that is equal to, yes I have written here, that is equal to mass of the system and acceleration of center of mass. This is with respect to laboratory frame of reference. Next, what is the kinetic energy of system of particles? So we are going to understand the system in terms of every particles of the system. Okay, we are understanding the position vector, velocity, linear momentum, the force acting on the system of particles, acceleration. Next, we are also trying to understand what about the kinetic energy of the system of particles when the system contains n number of particles which are not fixed. Not fixed means are moving independently in different directions. Right, here total kinetic energy of the system is equal to K1 plus K2 plus K3 plus and so on. This can be written as summation Ki. Kinetic energy of system with respect to laboratory frame. Yes, these are all velocities, masses with respect to laboratory frame, and even Vc is the velocity of center of mass with respect to laboratory frame. This can be written as kinetic energy means half mi Vi square, because this is ith particle, and here for the this summation, this I am rewriting like this, half mi Vi square can be written as Vi bar plus Vi bar. Now Vi is equal to Vic plus Vc. This we know. K is equal to summation of mi Vic plus Vc dot this. Let us expand with these two terms, dot product. Next, plus Vc dot Vic plus Vc dot Vc. Yes, this can be written as Vic square plus half, no, these two terms, right? A bar dot B bar is equal to B bar dot A bar. So dot product is commutative, so I am writing this 2 like this, plus Vc square. Now let us expand summation mi Vic square plus summation half mi into this Vc square plus, I am writing this middle term at last, summation half mi into 2 Vic dot Vc. So what I get is half mi Vic square plus half Vc square summation mi plus Vc bar dot, here Vc is fixed from laboratory frame, I am taking it outside, so summation 2 to cancel, summation mi Vic bar. We know summation mi Ric is 0. Similarly, summation mi Vic is 0. Why? Because summation Pic is 0. Already we proved, right? That is. So summation half mi Vic square plus summation, here this is equal to capital M Kic plus half m Vc square. This is kinetic energy of ith particle with respect to center of mass. So total kinetic energy of the system, K is equal to Kic plus Kc. This is kinetic energy of center of mass. So Kic is equal to kinetic energy of system with respect to center of mass, and Kc is equal to kinetic energy of center of mass. K is kinetic energy of system with respect to ground, means laboratory frame. Next, for two particle system, let us discuss, means the same discussion but only for two particle system. Here KIC is equal to K1C plus K2C, because we are considering the system contains only two particles, and half VIC square plus half M2 second particle, right, V2C square. V1C is equal to V1 minus VC. So V1 minus, this is center of mass formula, velocity of center of mass formula, that is equal to, you just go for it, you'll be getting this. Similarly this, just to substitute here, half M1, V1C is M2 into V12 bar by M1 plus M2 plus half M2 into V2C is equal to this, half M2 into M1 V21 bar by M1 plus M2 whole square. So here after expanding, if you take the terms M1 half and M1 M2 by M1 plus M2 whole square outside, you will be getting here M2 square, M2 term came outside, right, one more M2, V12 square plus here M1 V21 square. Next, but V12 is equal to minus V21 vectors, but their magnitudes are same but directions are opposite. Now KIC is equal to half M1 M2 by M1 plus M2 whole square. Here these two are same, that's why M1 plus M2 plus M1, and I am taking this term outside because both are equal, V12 square. Now this term cancel, half M1 M2 by M1 plus M2 V12 square. This is a reduced mass, this term, so KIC is equal to half mu into V relative square. Here V relative is independent of reference frame. Why? Because 1 with respect to 2. For two particle system, this is half mu into V relative square plus half capital M VC square, right? Next, here KIC is equal to half M1 V1C square, right, as per this from this equation, and similarly, and KIC is minimum when its differentiation is 0. Next, this is 0 differentiating, and M1 half into M1 into we can sorry, here extra term. Here square, here 2 into V1 minus VC into again differentiation of this minus 1 plus here 2 M2 into V2 minus VC into minus 1. So I take 2 outside and expand M1 V1 bar minus M1 VC bar, minus 2, remove minus 2, and here M2 V2 bar minus M2 VC bar. So you will be getting this, right? Now if you substitute this 2 in this one equation, you will be getting this, that is, when second reference frame moves with the velocity of center of mass frame, then kinetic energy is minimum with respect to center of mass. So this is the conclusion. Thank you.